I'm going to talk about the hardware abstraction layer, which we just saw in Stefan's example with a timer, for example. The timer was deriving from a base timer, which followed the pattern of the curious returning template pattern. That's basically our hardware abstraction layer. You know, in this timer base class, we're dealing with interrupts. We're defining the tags so that Kvasir start can connect the correct interrupt service routine to us in the base, and then we, you know, when an interrupt comes in, we sort it out. We look, okay, in the user layer, is there a function named onMatch with the proper tag? If yes, call it. If no, ignore the interrupt. It's absolutely clear what we have to do in that case. You know, we have to process the interrupt and then clear the flag, right? So we do it completely. There's also some other functionality which could be going on here. For example, the scaling of the timer, the initialization of the timer is going on, which brings us to a bit of a dilemma. The timer is a good example. We have very generic timers that just count up to a match and then reset themselves and then count up to a match. And then we have, you know, very exotic timers that have a whole state machine going on inside that are, you know, meant for motor control or pulse width modulation of low frequency sound waves, or, you know, just, you can do awesome things with these timers, but they don't have the same interface, obviously. So if we were to make, you know, one generic timer, then our generic timer, we'd have to dumb it down to the lowest common denominator of timers. So instead of doing a one-size-fits-all hardware abstraction layer, we actually went with a two-layer hardware abstraction. So the lower layer exposes all the hardware functionality, and then on top of that, we basically have an adopter pattern, which basically takes away functionality that isn't common to other timers. So in the lower layer, we have you know, all the initialization stuff and you know, hooks where the user can you know, add something to the default config, or can define a function named X that's called from the base. Things like that can make full use of the hardware's potential. And then on top of that, we have the upper layer, which basically turns it back into a set to go off in 3 milliseconds, yay, it went off timer, right? So, you know, here we have the lower level timer base, timer configs coming in. There are other defaults in the timer config. I mean, if you were to click on this and go to definition, then you'll see const expr variables for all the configuration parameters. So it actually is, you know, somewhat self-documenting code, at least in the sense that you know what to name your stuff. So you don't have to like memorize, oh, what was it user init with a big I or whatever. No, just look in the base. You can see what you can define in your derived class, which will then, you know, overshadow the base and therefore override the default behavior. And then, you know, upper layer, we haven't actually done much of the upper layer hardware abstraction layer yet. It's, you know, more sort of future stuff, but this is what I would expect it to look like, something, you know, similar to embed. Here I define a CDC, communications device, for USB, so it's basically just a serial port emulation. I give it my config object, I tell it which callback I want it to call when data comes in, and I can just write to it. And this would be the whole USB code, right? in my config object, I would, define my string of what are my capabilities as a USB device. The only thing I'd really have to specialize, because, part of this make CDC is, oh yes, it's a CDC, right? The only thing I'd really have to specialize in my config object is what's my vendor ID, what's my product ID, and what's the name of my device, right? And yeah, callback data comes in. Kvasir range is something that we worked on in the beginning and is not frozen yet, but it's actually almost always more efficient to use 2 pointers rather than pointer and size, or reference and size when you're dealing with a range of data. And it's definitely more efficient to pass ranges around rather than actually copying things around. Yeah, we will finish Kvasir range, which is kind of a lightweight pointers into a vector or an array, and then we can just use the C++11 range-based for syntax. Range has a begin and an end iterator, so we can put it here, and then we just everything we get we push into our state machine, whatever, right? That's sort of how I picture higher level Kvasir code to go. We're actually kind of getting into the future section here of the talk. Stuff that's not yet implemented but should be. Tubular how questions? Next part. Future work. There's the, I mentioned the boost metastate machine at the beginning. High level of complexity in the interface. This would be how you define the transition table of a state machine, basically, right? So we're going from stopped on the event play to playing, right? It's a CD player, right? This directly from the boost MSM example. This would be the example of a state. We can define an on-entry action, on-exit action. We can access the event and access the state machine itself. If we want to have access to data, we have to say, oh well, where is this data coming from? Well, it's coming from the state machine. But this is pretty confusing. I mean, we're making the user write template, right? That's kind of a public interface fail, in my opinion. I mean, the Boost MSM was written in a different era, right? It was pre C++11, and they did a very good job. I no disrespect to the author of Boost MSM, but even though the MSM is basically better in every regard versus Boost state charts, we use Boost state charts, and I would suggest Boost state charts because you don't have to write template, right? You don't get a terrible error if you screw this up. This would be, what I would implement as a state machine, will implement as a state machine. This is basically the next step in the Kvasir development. First, you define a million states. They have to be a unique type. Boost was, you have to make your own struct and put stuff in it. Basically, it's like a tag. What's in a state in automata theory? Nothing, right? It's just a place you are in a state machine, right? So if I'm representing a state, well, I want to represent just a tag. And the easiest way to get a unique type in C++ is a lambda, right? So this is the lambda introducer syntax and empty body, right? So it's a lambda that does nothing. We're never actually going to call it. It's just, we need a unique type to tag each state. Actually, this part, I didn't even include the Boost equivalent of defining all the states because it would have been like 4 slides. So, and all the events for that matter. Event, again, is a tag. Event could have data in it. In the example a couple of slides ago, with the USB, the characters coming in over the USB were going into an event, right? So an event can carry data into the state machine, in which case we'd use a struct instead of a lambda and just give it data members. So this would be how I define the state machine, using the context for metafunction syntax. So SM is my type, auto, because, you know, I can't write the type of it. The type is some giant jumbled up combination of all this. So I just write auto as a user, state machine namespace, factory function make, and then I give the factory function all my transitions and all my on entries and all my on exits in sort of function call fashion, and I have to find a complete state machine, right? So I'm defining a transition here from stopped on the event play to playing. I could also add a comma and put in transition actions, put in guards. It's actually pretty easy to disambiguate behind the scenes what's a action, what's a guard. Action doesn't return anything, returns void. Guard returns a bool, right? So you can put as many guards as you want in there, put as many actions as you want in there, any order, I don't care. I'm going to figure it out behind the scenes, and you're going to have an easy syntax, right? So from state, on event, to state, and then whatever else you want to put on there, right? The on entry and on exit actions, we can also define pretty simply. We go from, you know, our stop state on entry. Okay, I commented it out just like in the boost example, but you could, you know, take away the comments and it would say, I'm entering state, stop, I'm exiting stop. It's just a lambda, right? So, you know, to play around with our state machine, post an event to it, post play to it, post stop to it. We can check which state it's in. So that's, you know, okay, that's the boost equivalent, but that's not really real world code, right? That's, you know, you don't write a CD player, right, with all these events that are empty. State machine's also empty, it just has a state, right? In a real world case, you know, you'd be defining a state with data in it. So my state now has two data members, and my event also has a data member. Okay, in this on entry example, on entry of my state, I want to take the data that's coming from the event and put it in my state, right? So I take this variable context, and notice this is auto. Auto in the parameters of a lambda basically means that this lambda is turning into a functor object with a templatized overloaded function call operator. So context can be any type, but I don't really care that it's any type, you know, because at this point we don't know what all the parent states are, what kind of data they have, and all that kind of stuff. We can't know when we're writing this context, nor do we want to write what type the whole state machine is, right? We just get, this is basically a reference and a bunch of meta information wrapped up together. This context is basically access to the whole state machine's data, all the active states. And so we can use this get state, get context. Actually, I think we can just shorten this to get. You know, this interface is very early. Just say, okay, this is a tuple of all states, would probably be the easiest mental model to use this. So we just say get from context my state, and it gives us a reference to that state, and then we can access I, and then the event, well, we fully typed the event, so we can just take I out of the event and put it in there. Much easier than in Boost MSM. Under the hood, it's doing pretty much the same thing. I mean, this polymorphic lambda syntax is actually only supported in C++ 14, but GCC 4.8 supports it, and all the tool chains for the embedded field are either not GCC or GCC 4.8, 4.9 by now. So this is, you know, potentially supported. We're doing a transition. Well, with transitions and transition actions, the question is, there's kind of an ambiguity of where the action actually happens. in automata theory, the transition action happens outside of either state. Not in the old state, not in the new state. To me, that seems kind of stupid because, you know, there's no disadvantage of being in some state. And we may want to access data in either the old state or the new state in the transition action. Otherwise, the transition action is actually kind of pointless because it only has access to either super states, like parent states that are not affected by the transition, and the event. But that doesn't seem very useful to me. So most state machine implementations do it in the old state. So you're transitioning out of a state, the transition action is going to happen in the context of the old state. With the Kvasir metastate machine, we're going to give you the choice of both. An on-entry action can be specialized. Here we defined my event. Well, what if we get into my state with my other event, some other event type? Then this lambda's call syntax wouldn't work. Well, on an on-entry, you can either do it generic or just leave out the parameters as far as event, and then it would be for all events. Or you can supply multiple lambdas, each filtering for a different event, and therefore have a quasi-on-transition action which happens in the new state, right? Therefore, I'm going to go with convention and say the normal transition actions, old state, event, new state, action, the traditional actions, they will be done in the old state. So you can do either one. This is a guard. You can see it's returning, a Boolean, whether I is the meaning of life, right? It'll be interpreted as a guard. I could switch these around. The meta program down below will figure it out. You can query for a return type, basically, using something called asFINY, which is above the realm of this talk. It's a meta programming technique where I can make something fail and then notice that it failed. I could also make a lambda with that's generic, that would doesn't have an event parameter, for example, which would or works with any event parameter, which would take every event that is not my event. That's also a little more tricky, but also possible to do with meta programming. So we have this awesome functionality in our state machine, which is actually not that awesome. It's just a bit prettier code for stuff that already exists. Other state machines do this. The Qt has a state machine that works kind of similar to this. It's hopelessly slow because it uses a lot of indirect calls, but mostly because it's generated at runtime rather than at compile times. But it serves its purpose. Still, state machines are not used very often, and especially in an embedded field, it's actually really important that we use state machines a lot more than we do, because if we use a scheduler as a kernel, then we essentially don't have the problem of stack overflow on one stack. We have the problem of stack overflow on as many threads as we have, plus interrupts stacks, right? So we, first of all, we waste RAM because we don't have max stack depth. We have max stack depth of each thread all added together, plus max interrupt stack depth, plus 100 bytes of work registers and system registers and stuff that you have to cache in the meantime, right? So if you're running a scheduler, then you lose on RAM, right? You use more RAM than you would in a run-to-completion kernel equivalent, right? You also essentially lose on speed because you have to do all this context switching, right? That's not buying you anything really. So you lose on speed, you lose on power, you lose on RAM use. I'm not really sure if you lose on flash size versus a typical multi-threaded versus run to completion kernel. I don't think it's all that important because as much flash as Kvasir saves you, flash is probably not going to be your design constraint. Probably the most important thing that schedulers lose on is worst case scenario reliability. Because if you have many stacks, then the stacks grow into either each other or global variables or the heap or something, right? If you only have one stack, you can put it in RAM such that it grows towards unaddressed memory. And if you grow into unaddressed memory, you are guaranteed to detect stack overflow, right? You will get an interrupt as soon as you leave addressable RAM. What you do at that point is, probably pretty drastic. You probably reset the system or something. I mean, what else are you going to do? But, I mean, I'd much rather my Toyota die once every 150 years on average than floor it once every 150 years on average, right? I mean, you have a guaranteed action that happens on Stack Overflow, which makes your code so much more reliable. I mean, if you're in, say, the chemical industry, or you're, doing railroad management systems, or embedded systems in that domain, we're usually like, I don't know, built in the 70s or something, and we laugh about it, that there's this thing that basically, tests one sensor and turns on a fan if it gets higher than temperature X and costs $1,000 and is this big. But this is why. I mean, it works, and it's worked for 40 years, right? We actually have to prove that our, $3 Cortex design can replace this thing and always work. The always work part is the hardest part, right? So if you can guarantee worst case scenario, then you've definitely got a leg up against these systems that are older than me, right? The other thing that you gain from run to completion kernel is determinism, deterministic behavior. If you have something running at the highest priority interrupt, then you can prove in both cases it's going to happen pretty quickly. I mean, at the end of the day, it's going to happen for the length of time that you've turned off the highest priority interrupts. That's the maximum theoretical latency. And if you don't do that, if you never turn off the highest priority interrupt, you'd have to have some thread synchronization system for that highest priority interrupt to actually talk to anybody if it is never turned off. But that's also possible, lock-free queue or something. Then you can prove that at the highest priority, I'm going to react immediately. But what about like the second highest? I mean, as soon as you have more than one timing deadline, which is really short timing deadline, as soon as you're not the highest priority, it gets hard with a scheduler. If you're not an interrupt, it's really hard with a scheduler. It's like, because scheduler, not only, you still don't have the guarantee with a good scheduler that the highest priority thread is going to go as soon as there's a reason for it to go, right? I mean, it could be that the highest priority thread has been starving all these other threads, and then right at that moment, dynamic priority decides to throw in a lower priority thread, right? Your guaranteed longest time before your event gets processed is typically much higher in a scheduler for anything but the highest priority event. With a run to completion kernel, you can go down the line. You can say, okay, how often can this occur? How often can this event occur? How often can this event occur? Go with your static checking tool, figure out the longest path that each one of these can take, add them up and say, oh, look, there's still a window. So within, a millisecond or 10 milliseconds or 100 milliseconds, I'm still guaranteed to have my event processed. So my crane won't tip over, You know, my stabilization thing is maybe running after my, I don't know, don't let the motor burn up, and another, I mean, in embedded systems, we see all sorts of designs where we basically have one processor per sensor, right? You know, we have very, very, very simple designs because we have problems with this guaranteed latency, which then just defers the problem onto guaranteed latency over the bus that connects these systems with each other, right? So we're not really getting rid of the problem. It would probably be, I mean, it'd certainly be cheaper if a lot of that was running in one processor, but it would be faster time to market, easier design, so on and so on and so forth, but scheduler just kills it, right? You know, plus scheduler, in my mind, doesn't win on work versus power either, just because it's probably executing more assembler instructions. It's spending less time sleeping. I mean, with the scheduler, oftentimes there's not really a logical point to sleep. If you've got threads that are polling, you never really go to sleep. Whereas with run to completion, as soon as I don't have events in the queue, I can go to sleep, right? And save power. So run to completion basically wins on everything except for programmer productivity. A lot of people don't really know how to write typical stuff as a state machine. And you have to write as a state machine for it to be run to completion. I mean, if you're doing something, then sleeping, then doing something, then sleeping, that's also kind of a state machine, just not quite, right? I mean, at the point where you sleep, you've completed that part of your task, go on, do something else, come back. At that spot, you know, the scheduler has to save the entire state, has to save all the work registers, all this other stuff. A state machine will only have to, you know, save one integer if that's where you are in your execution of that path. So why is almost everything written for a scheduler, right? I think one of the reasons is we don't have a good, easy to use state machine framework. Writing state machines is, at least for many, people, this idea came from a discussion I had with Woodruff and Weitjen that said, well, you know, there's this LCD controller. I don't think some of my students would be able to easily write code for an LCD controller in the form of a state machine, right? And, you know, he teaches people in this field, so I take his word for it. Okay, that's a problem, right? So this is part of the LCD controller, right? So this is kind of the you know, some code I found on GitHub, which is a class that talks to this LCD controller. So we got toggle enable. Basically, we're waiting, we're setting a pin, we're waiting, we're clearing the pin, we're waiting, and then, you know, reset operation is we're setting the port direction to output, we're clearing a bunch of pins, we're setting data to 3, which is, I guess, the reset command. I'm just guessing here, and then we, you know, call this whole dance of waiting and clearing, and then we wait again, and we call this whole dance again, and we wait again. So it's kind of a function calling a function calling a function. Well, how would you put that into a state machine, right? It is a little complicated. Plus, this is only like 10% of the code. There's a whole lot more there, right? It's definitely state machinable, but you know, the code in state machine form would look nothing like the code in this form, right? In this form, it's kind of easy to reason about it. And one of the reasons why it's kind of hard to translate this into a state machine is because state machines usually, they expect to get any event at any time. Whereas this is much more linear, right? We do this and then we wait. We do this and then we wait. And then we do this and we wait. And if some other event comes, well, we're not even looking for any other event, right? We're on this linear task, and, you know, going through this, we're gonna wait for what? 12. We have 12 different waits, right? We got 3 here, and the 3 here we call 3 times. So no, we got 15 different waits. So it's basically 15 different substates, if you will, and the timer event is taking us on a transition from one state to the next. And in the on entry in air quotes, we're setting a pin, we're clearing the pin, we're doing very, very, very simple stuff. And if you were to implement this thing in Boost Metastate Machine or in Boost State Charts, this would be pages and pages of code just for this little snippet here, right? So that's really the reason why we're not programming things in state machines in a run to completion manner. It's hard, right? And it's not really. It's far from our own mental model of what's happening. And the whole idea of metaprogramming is to allow people to express things close to their mental model, and then under the covers turn it into whatever you want. Whatever you can prove is the same functionality, just faster, right? So what I came up with is, here we have our little function snippet, enable wait. It takes a context, which is basically the whole state machine. Oh look, here I'm using the new syntax already. Fail. Anyway, so this get is the same thing as get context in the old one. So it's basically assuming this is a tuple of the whole state machine. So somewhere in the state machine there's a state called root, and I don't think I even included it on the slide, but in root has a member function set timer, and we can set timer events that are going to be posted to us in the future. This is just a tag for a functor of this type, right? We define a guard. So in this functor, it will basically return true if it's an EV timer event. And if it's not an entire EV timer event, this guard is not applicable. So it'll basically ignore every other event. This is just an alias to sequence point, so I don't have to write register scope operator sequence point all the time. So now it gets interesting. Toggle enable is this function. And here I'm basically programming it in what I call an action chain. Rather than saying, oh, I have all these states and I have all these transitions between them, what about the special case where I have a chain of states, where I'm going from state to state to state to state, and it's just one direction, and if I fail, maybe there's a rollback, but it's linear. State machine code is not usually linear. So basically, I have a variadic function. Chain can take as many actions as you want. So basically, you throw at actions, right? Enable wait is an action. Enable wait is this thing, right? The action sets the timer. And then a guard. So as many actions you want, they'll all be executed once after another. And then you wait until the guard is fulfilled, until you get an event that you can pass to the guard, and the guard says true. It can go on. And then our next action, well, this is just a register action, right? This is something that we could give to apply, right? This is something you could have seen in the other code, apply set LED pin, right? Since we're in Kvasir, we're the Kvasir metastate machine, we understand what a register action is. User doesn't have to write apply. We can just execute that. And then we do our enable wait again. So we basically set the timer again. Then we guard and wait for the timer. Then we clear the pin, set the timer, wait for the timer. So it looks like we've defined a function, right? I mean, if you look at the internals of chain here, and the internals of toggle enable up here, sorry, the toggle enable chain there and the toggle enable here, it's basically the exact same thing. It's just we're using Kvasir to set and clear the pin, and we've added guards. I mean, this wait here has turned into the request of a timer event in the future, and a guard waiting for that event to actually happen. So how we model this, when we put it into a state machine, this chain, is whatever state this chain occurs in gets a bunch of substates called substate 1, substate 2, or probably substate with a template parameter 1, 2, 3, 4. I mean, states in my state machine are just unique types. Any unique type will do, right? So I could just, create a bunch of meta types and turn this directly into state machine stage with transition actions, or on-rent reactions, whatever ends up being good. The other thing I can do is I can create another chain, and from within this chain, I can call the other chain. How I implement that under the covers, I could either make like a history state, in which case I would save flash at the cost of RAM. I'd have to remember in the history state what I go back to. Or I could just inline it and make it just a huge chain of states. I mean, I'd be using a 32-bit integer as a index of which state I'm in anyway. There's a lot of room there, right? So yeah, I mean, maybe I'd generate 40 states with very minimal actions between them. So be it. It's all auto-generated under the covers. The user doesn't have to actually write 40 states.
The chain? And put the chain into the state.
Yes, here's the example of that, right? Okay, here I've got my state machine, the super state, i.e. the parent state of all states. This is probably a pattern that's going to happen often, so I gave it its own keyword, super. That's this root, so that's what we're accessing here to set the timer. So we have to make sure that this, whatever type this root is, has a member function set timer, right? And then our initial transition from nothing to idle says call reset. Resets this thing. So we're calling the chain as a transition action, right? So what does this mean? This means we don't actually truly initially transition to idle. We transition to substate 1 of super, which is our auto-generated state, and we go through all those states, and eventually we land in idle when we're done, right? In this case, we obviously can't fail, because what do you do when you fail in the initial transition? But there's not really a way for this to fail anyway, right? We just go through it. I mean, it could wait forever if the timer never sends us its event, but that's a design error anyway. So we can't really guard against that. Yeah, we could also do an on entry is a chain of states. We could do a transition action in this case, on exit, chain of states. If it's an on exit, well, we don't actually transition from that state to the state that we think we transition to. We actually transition to, substate 1 of our chain of states, and then once we get to the end, that actually goes to the next state. What we could also do is add rollback, commit and rollback semantics to it. So going forward, I have all these guards. Well, I could also say in my lambdas, in my action lambdas, I could just call this function called fail. It is just part of context, right? So context.fail. Context.fail sets a bit. Every time I come out of an action, I check this bit. Did I fail? And if I did, then I go through all the actions that came before and look at all their rollbacks. So exactly as far as I got, that number of rollbacks, or all the rollbacks before that, I can roll back. The rollback can't fail, so you got to program it so it can't fail. But yeah, that would be entirely possible. The caveat, the thing that's actually really hard to do, luckily this code has no ifs in it.
Question.
Yeah.
The rollback in this context, how would that?
In this context, there is no rollback.
Yeah, that's what I was
But here in my chains, I could call a function called rollback and give it a lambda and put it, say, here. And as soon as I pass that rollback and then fail, then that rollback will be called. So I could just put rollbacks in wherever I want, right? in which case it would probably then be better coded than the threading equivalent and more efficient, right? Because you've got easy syntax to do rollbacks. You know, the information that the rollbacks use to do stuff would have to come out of the superstate or root or whatever, but that's usually where usually that's where users put state anyway, you know, some superstate of the state machine or their parent state or something. Putting data in the state is very short-lived because as soon as you transition, then that data is gone, right? If we have this pattern, if something wait, right? That's just something that's really hard to go back to because you're kind of in the context, right? You can't say, oh, well, everything before this wait, I'm going to turn into a lambda, right? I can't have half an if in the lambda. So this is hard, but there's nothing stopping us from making a chain if, chain else, right? I mean, we're going towards a domain-specific language here, but if this is the only other caveat that I figure out, then I'm definitely programming it this way. You know, chain if takes a lambda which returns a bool, right? If true, I do whatever happens here, right? You know, since I can turn all this into a state machine and it's actually very, very close to code you would normally write in a threaded manner, I think it wouldn't be too much syntactic complexity and would be a big benefit. So it would pass my chart test.